Okay, we're going to do, I will do the beginning of this worksheet with you in this screencast so that you can turn this in for class on Thursday. We're going to apply what we know about circular motion to actual situations. A couple problems here with cars going through circular, a valley and then the top of a hill, but basically circular motion. And we're going to try to figure out what forces are acting on the car based on what we know about the unbalanced force and speed and the radius of the turn and how it affects the unbalanced force in circular motion. So it says a car travels through a valley at constant speed. I'm just reading through here. And though not at constant velocity. How is it possible? How is it possible that the car moves at constant speed but not constant velocity? I'm going to let you answer that because we've talked about that in class a few times now. So I hope you have an idea of that. Then it says construct a qualitative motion map for the car. Qualitative is not based on numbers, it's based on a description. And it wants a motion map. So I'm going to start when the car was back here, moving on, in a straight line, and then it begins to go down the hill here, and it's changing its direction at every instant. But notice how I'm drawing the vectors the same length because it's at constant speed according to this according to the description. So that would be my motion map for the car. And the question is the car accelerating? Well, you might say no because the length of my arrows are all pretty much the same. I'm just putting check marks on them because it looks like they're all the same length. So you might say no, but they point in different directions. All right. So it says, what's the direction of the car's acceleration? I want you to answer that question, because it's going through a circle, and we know that when an object is in circular motion, the car is going in a circle in this direction, and the center of that circle is up here. We know that the acceleration is always pointed towards the center of the circle. Okay, so answer that question, and then we'll get to part D on the next slide. So we're going to construct a qualitative force diagram of the car. At the moment, it's at the bottom of the valley, and it wants to know, are the forces balanced? Okay, so let me draw a force diagram for the car at the bottom of the valley. I'm going to do it over here. Actually, let me draw it on the bottom. I got a little more space on the bottom. I'm going to shrink this down a little bit. Draw it down here. I know there's always an MG, right? So there's my car at the bottom of the valley. Now I know the acceleration is pointed up. How do I know that? When it's at the bottom of the valley, because up is towards the center of the circle. The radial acceleration always points along the radius of the circle, and when it's at the bottom of the valley, that means the center of the circle is straight above it, so the radial acceleration pointing along the radius is straight up. Well, if the acceleration is straight up, that means the unbalanced force must also be straight up, because the unbalanced force and the acceleration always point in the same direction. Well, if I only have two forces, the force of the earth pulling down and the normal force of the road, and the unbalanced force is pointed up, that means the normal force of the road on the car must be longer than the gravitational force. So I draw it like that. So that's the qualitative force diagram. Are the forces balanced? I'll let you answer that and answer this question. Justify in words the relative sizes of the forces. Why is the normal force greater than the Earth's force? You have to answer that question based on the description I just gave you. Well, now it gives us some numbers. It says the car's speed is 25 meters per second. I'm going to call that V. Notice they use the word speed. It's not necessarily in a direction because the direction is changing. The speed is 25 meters per second. The mass of the car is 1,200 kilograms. And the radius of the valley is 25 meters. what's the unbalanced or net force acting on the car. It's not asking us what the normal force is or what the mg force is. It's not asking us for those individually. It's asking us for the unbalanced force. Well, remember, the unbalanced force is the difference between big minus little is n minus mg. And in the case of something moving in a circle at constant speed, that's equal to m times ar. And you might remember that AR is equal to V squared over R. So in this part here, a quantitative force diagram, I've got to first solve for the unbalanced force in part E, and then I can figure out what N and mg are. First of all, I know what mg is, because if the mass of the car is 1,200, then mg is just 1,200 times 10 newtons per kilogram. That is 12,000 newtons. Okay, well, now let's find the unbalanced force. It's equal to m times v squared divided by r. So my unbalanced force is 1,200 times the velocity squared, 25 squared, divided by the radius of 25. Oh, they made it easy on you guys. So you just cancel out one of those 25s. So 25 times 1,200 is the unbalanced force, or 30,000. Units are newtons. So 30,000 Newton unbalanced force. So now I'm going to take this equation here, solve for the normal force. Normal force equals F unbalanced plus mg. I've moved mg over to this side. I've added it to the other side of the equal sign. Over here, actually. So I add it to both sides. The unbalanced force is 30,000 newtons. mg is 12,000 newtons. The normal force is 42,000 newtons. So that gives us the difference between the n and the mg is 30,000 newtons, which is exactly what it's supposed to be, right? Based on m, v, the speed squared, and the radius. All right, so that's how you would apply what we've learned in the experiment analysis that we did. Page 2 is really similar to page 1, only the car is going over the hill. So now the center of the circle, center of the circle is down here. So your force diagram is going to look a little bit different, because now the car is on top of the hill instead of on the bottom of the hill. So the normal force and the gravitational force are not going to have the same magnitudes as they had in the first. At least the normal force won't have the same magnitude. The gravitational force, it doesn't matter if you're moving up or down over a hill, the gravitational force is the same, but the normal force will change in this situation. So try to do this one based on what you learned in problem number 1. And I'll go to the next page. Okay, so this one is a little different. This is a car that's going around a turn with, in part 1, it's a flat turn, and it's coming out of the page towards us, but it's turning to the right on our page. So the center of the circle is somewhere over here. And in this case, you've got a little bank to the road like a NASCAR turn. So that's a little different situation. Let's do one at a time. So roads are banked or tilted in curves in order to make turning a car at high speeds safer. For the situation of an unbanked road, draw a force diagram for the car coming toward you as it's turning. Which force provides the force needed to make the turn? Well, let's draw a force diagram. Our object of interest is the car. So I'm going to say I know the earth is acting down. I've got mg, and I've got the normal force acting up. There's no acceleration up or down, so those are equal. But it's making a turn, and I know there has to be a force that is directed towards the center of the circular turn, and that force in this case is friction. Friction is what allows the turn to happen. If you've ever had the experience of turning your steering wheel during a winter icy day or on a winter icy day when your tires are on ice and there's not enough friction, the car just keeps going straight. So it's basically friction that allows that car to turn. So that force diagram looks like that. Now you've got a banked road. Draw a force diagram for the car coming towards you as it's turning with the banked road. This is down here. Oops, sorry about that. As it's turning, identify all the forces and components that contribute. So this is a little different. So now I still have mg straight down. I'm going to draw it about the same length. But now the normal force is up at an angle. Okay? So let's label that. And I still got some friction. So I still have a component of friction in that direction. Now I've got the radial direction and I've got the y direction. Notice how I point one of my axes along the radius of the circle. The center of the turn is still a horizontal circle. It's just that the road is banked at this angle all the way around. But the center, the car is going, if it was a perfectly circular track, it's moving in a circle in a horizontal plane. So I actually have to draw components for the normal force now. So I've got a y component and I've got a radial component. So friction's got some help now from these will be equal here. The unbalanced force in this case is friction plus the y component of the normal force. All right? To make this thing go in a circle. Here the unbalanced force is only friction. So the banking is actually letting you go faster because not only do you have friction helping you, but you've got a component of the normal force which is perpendicular to the surface of the road. And since the road is banked at an angle, that normal force is up at an angle, so that makes it have a radial component that helps you to make that turn. That's why they bank those turns in the NASCAR races. Okay, I'm going to let you do the yo-yo problem number 4 by yourself based on what you've learned so far in this screencast, and I'm going to ask you to turn this in before class on Thursday. Have a great day, guys.